morning will be contributed from the University of Louisville, the identification of CN bond-breaking sites with isotopic labeling by J. Marzari, who will give the talk, S. Rajagopal, and R. Miranda.
Today's presentation is going to be identification of carbon-nitrogen bond-breaking sites using diffuse reflectance IR spectroscopy and isotopic labeling. First of all, what is hydrotina? It's a catalytic process in which nitrogen, sulfur, oxygen, and metals are removed from organic compounds present in feedstock. The removal of sulfur has been optimized and the catalysis is well understood. However, there is a need to design a suitable catalyst for the nitrogen removal. This reaction is called Hydrotina hydrogenation. So if we know better the mechanism of Hydrotina hydrogenation, we are going to be able to achieve this goal. In the mechanism, the carbon-nitrogen cleavage, that we think that is the rate limit instead, has to be better understood. Now, let's see which are the mechanisms postulated and approved so far, and they are three. First of all, hydrogenolysis, that is thought to be that occurs in the presence, or thought to occur in the presence of metal sites. Hoffman elimination by E2, thought to occur also in the presence of bronze acid sites, Lewis basic sites, and the nucleophilic attack at the alpha carbon followed by CN carbon-nitrogen cleavage. That is also thought to occur in the presence of other nucleophiles. Now let's go deep in the mechanism. First of all, hydrogenolysis. What we see, first of all, we have an intermediate alkene, methyl alkene intermediate, and then the addition of hydrogen in the alpha position, and then the carbon-nitrogen cleavage proceeds. Elimination, also called Hoffman elimination, proceeds in the following way. Proton coming from the surface, quaternize the nitrogen, and then a hydrogen coming from the beta position goes to the bronze state, to the Lewis space. And finally, the nucleophilic ring opening is also hydrogen quaternize the nitrogen, and a sulfhydryl group bonded to the alpha carbon, and the carbon-nitrogen bond cleavage proceeds. Now, traditionally, this mechanism of hydrogenolysis is well approved. However, in 1979, Levin and Nelson proposed that together with hydrogenolysis or parallel hydrogenolysis, bronze acid sites or an acid-base catalysis proceeds with an elimination mechanism. In 1983, Line proposed that only metal sites catalyze hydrogenolysis and doesn't give any credit to the acid-base catalysis. Since in our we did or performed our experiment with no sulfide catalyst, this mechanism, we are not going to talk about this mechanism. Now, which are the objectives of our work? General objective is to study the feasibility of the Hoffman elimination mechanism carried out by acid-base catalysis. Now, particularly, we are focusing in demonstrating that the ring opening step can be catalyzed by bronze acid sites. Then also we want to show that how piperidine interacts with the acidic surface, and finally to display that there is an interaction, the interaction of between the OH surface group and piperidine leads to a labile beta hydrogen. For that, first of all, we proceed with, we show the Hydrotina hydrogenation of pyridine. First of all, it is well known that a total or partial hydrogenation of the ring is necessary to then to proceed to the ring opening, either by hydrogenolysis or by beta elimination. So we did the reaction using pyridine at atmospheric pressure, 420 degrees, over different loading molybdenum on different supports like silica, alumina, and silica alumina that we know that they have different acidities. And we found that the larger activity, the larger conversion towards hydrocarbon was achieved when the support was silica. So we tried to correlate this result with, first, with the coordinated unsaturated side coming from the metal. And for that, we did an experiment that is low temperature oxygen chemisorption, and approximately it correlates. I forgot to show before. Oops, that the largest conversion was achieved when the loading of molybdenum on the catalyst was 4%. Also, I want to point out that during these reactions, the amount of molybdenum in the reactor was kept constant. Now, going back to low temperature oxygen chemisorption, we see that there is a certain correlation with the data that I showed before. However, the largest chemisorption was achieved for 8% molybdenum on silica, not 4%. So there has to be some other effect that has to be included in the reaction. For that, we studied the acidity of this catalyst. So, even for example, 8% molybdenum, but I'm interested only in the bare support. It was found when we chemisorbed ammonia on the catalyst, the largest chemisorption was achieved when the silica concentration on the support was 25%. We have to remember in here that ammonia measures total acidity. That means Bronsted acidity and Lewis acidity. Since we want to try to demonstrate the effect of Bronsted acidity in the reaction, we have to go to another technique as he mentioned before. That is the chemisorption of pyridine using diffuse reflectance IR spectroscopy, and then measuring the area under the peak of Bronsted side and under the peak coming from Lewis side and taking the ratio. And it was found that the largest Bronsted-Lewis ratio was found when the concentration of silica on the support was 75%. This is in good agreement with some other literature. This is not really new. So now, the question to answer the first objective, is the reaction possible only with Bronsted acid sites and no metal functions? The answer is yes. We did perform the reaction of piperidine. We submitted only with the bare supports coming from silica, from alumina to silica, and varying the concentration of silica alumina, and it was found that first of all the denitrogenation occurs, and second that as the acidity was increased, denitrogenation increased linearly. So there is a straight relation between Bronsted acidity and denitrogenation. Just to simplify and summarize what I have just said, this is a good scheme. Total acidity doesn't correlate with conversion, denitrogenation conversion. However, Bronsted-Lewis ratio does. In order to answer the second question, that is how piperidine, the interaction of piperidine with the surface, we started doing some diffuse reflectance IR spectroscopy using a controlled chamber, controlling temperature, pressure, the flow of gases. And starting in this transparency with silica catalyst and using different loadings of molybdenum, we found the traditional OH peak at 37, 40, 45. And something that is interesting from here is that as we increase the loading of molybdenum, the concentration of bronze of OH group of the surface decrease due to the interaction with molybdenum. Now, we achieved the exchange with D2 at 400 degrees, and we found the peak at 2757 centimeters, showing that this peak is the OD group. Now, this is showing, and this is not new, that silica just exchanged with D2. So, now going into our experiment, we took a pair silica, we flow it with hydrogen at 400 degrees, we exchanged with D2 at the same temperature, we reduce the temperature, we did vacuum, we set the pulse of piperidine under vacuum, and then we raise the temperature. What are the conclusions that we can take out of here? First of all, piperidine interacts with the surface. How strong interacts with the surface? Well, for this spectra, very weak, because piperidine dissolves immediately once we raise the temperature. And what we can see also that there is a regeneration of the OD groups. So no D2 has been evolved from the surface once we raise the temperature. Now, we took the same support, but we loaded some molybdenum, and we did the same experiment. What we found was the following. We reduce the catalyst, we flow with hydrogen, we change with D2, we lower the temperature, we did vacuum, we send the pulse of piperidine, and we raise the temperature. What we found was that piperidine, yes, interacts with the OD groups on the surface. However, when we raise the temperature, there is still some piperidine on the surface, saying that the interaction between the OD group or the OH group that have been exchanged with OD is greater than in the case before. Something that I forgot to say in the previous one is that piperidine also, what we can say from here, mainly interacts with the OH group that have been exchanged with D2. Now, the last observation that we can take from this transparency is that when we raise the temperature, there is some piperidine that has been evolved from the surface, but there is no such regeneration of the OD groups that were before. So that is saying that also some D2 is evolving from the surface once we raise the temperature. So the following transparency, what we show is that this OH group can be regenerated. What we did, we took the same catalyst that we took before, 8% molybdenum silica, we flow it at 400 degrees, reduce it, flow it at 150, make vacuum, send the pulse of piperidine, we raise the temperature, so some piperidine is still on the surface. Then we flow hydrogen at 150 degrees, there is some regeneration of the OH group. And at 400 degrees, there is an almost complete regeneration of the OH group on the surface, and piperidine has almost completely evolved from the surface. Now, just to simplify with what I have just said, this is a very simple model. When we have silica, we have the binary catalyst, the OH group of the surface, we change with D2. Some piperidine comes interact weakly with the D2, and then we raise the temperature, no absorption and no D2 has evolved. Now, in the case of when we have molybdenum on the surface, it's different. We have the bare catalyst, we have the exchange with D2. Some piperidine comes and interact more strongly, and then when we raise the temperature, some D2 has evolved, and there is still some piperidine on the surface. Similarly, we did the same experiment with molybdenum on alumina. The interpretation is more difficult since we have 5 different kind of OH groups on the surface. So we have a broadened band for our OH group, but however, the same is that similarly we find there is an exchange. Also, there is a broadened band. There is no one band, like in the case of silica. Lower the temperature with this vacuum, we chemisort piperidine. Excuse me, with some piperidine. But now what we are observing is that all the groups that have been exchanged, not all of the groups have been. Can say piperidine does not interact with all the OB groups that have been exchanged. Excuse me, OH groups that have been exchanged with B2. So then we rise the temperature, and we observe that there is still some piperidine on the surface. Similarly, going to silica alumina, molybdenum and silica alumina, we find the peak coming from silica, the broadened band coming from alumina, the exchange, also the exchange OD coming from silica, and the OD is coming from alumina. We send the pulse of piperidine. Also, piperidine interacts mainly with the ODs coming that have been exchanged with B2, but we see that the silica peak, the peak coming from silica has almost disappeared, while the peak coming from alumina has not disappeared. We have to remember that alumina has some of those OH groups coming from alumina are basic, so piperidine is not going to interact with another base. Now, in order to answer the third, or to give a certain explanation to the third objective, if the alpha hydrogen is labile or not, we took sample of the piperidine that was evolving. We took sample of the piperidine that was evolving from the control chamber in the diffuse reflectance and spectroscopy, and we took it to an MS mass spectrometer. And what we found, I'm going to show it later, but this is a general mass spectrum of piperidine. The main group, the main peaks that show up that I'm not showing here are 29, 30, 43, 44, 55, 56, 57, 70, 84, and 85. Now, keeping in mind these numbers, let's see what we found. Okay, none of them. Mainly the last two, 84 and 85. Okay. Keeping in mind this, some of these numbers, we found that for the lower masses, there is no change. However, well, the change coming here because we have 84, 85, and 86. That means there has been an exchange with with the hydrogen coming from piperidine. Now, where is that hydrogen? Where that hydrogen has gone? So, taking this analysis coming from mass spectrometer, spectrometry of heterocyclic compound by Porten and Bata, they show this following analysis. Now, if we want to analyze where it goes, to the nitrogen, to the alpha, beta, or gamma position, to analyze if it goes to the nitrogen or to the alpha position, we can analyze this kind of, this result. We see that it's much 30. If that the D2 has gone, D2 has gone to this, one of these positions, we should have seen 31. We haven't seen that much. So it hasn't gone to those two positions. Now, what about gamma? So we follow this mechanism. We see a release of sulfhydryl group. A release of a methyl group in the beta position, and the gamma group is still in there. We should have seen 71. It didn't occur. So what it's telling us that the proton, or the proton has been exchanged, the D2 has been exchanged with the proton coming from the beta position. So that could help us in figuring out, in determining that if this mechanism is, elimination mechanism is possible. So we see that when piperidine interacts with the OD coming, ODs of the surface, the beta proton of the piperidine is labile, and that is shown by the exchange. So what is showing at the same time that the elimination mechanism is a feasible mechanism for the Hydrotina hydrogenation and for the carbon-nitrogen bond scission. Finally, I would like to acknowledge these following institutions that funded this work: the Department of Energy, the National Science Foundation, and the Commonwealth of Kentucky by the EBSCO program. Thank you very much.
Are there any questions? Bert?
I didn't remember all the numbers when you told me that. But it seems to me that 84 and 85 are all deuterated, isn't it?
We have 84. The normal spectrum is 84 and 85.
Yeah. And so that would say that you essentially have per deutero pyridine, is that not correct?
Yeah, I have this, the piperidine, the piperidine that is evolving from the chamber has been deuterated, but where has that deuterium gone? And that was what I tried to find out in the lab, in the last slide, in the last transparency. We found that it went to the beta position.
But if it's per deutero, it went every place. If the mass is 84, that corresponds to deuterium being substituted at every carbon, doesn't it?
I get your idea. 84, 85, this is going to go much better. Yeah. The mass of piperidine is 85, it's not 84. So there are two ways of fragmentation. One way of fragmentation is by using a proton, and this is the main mechanism in the fragmentation. So it's 84. But the main mass, the mechanism called that here are called B. What it happened really at the beginning is just a transfer of electrons or protons inside the molecule. But the main the molecular weight of piperidine is 85. So if we have one T2, if we have a deuterium absorb exchange with piperidine, in piperidine we should have 86. I don't know if I have answered your question.
Any other questions? Thanks, guys. Very interesting.